Last time we talked about some stuff, I think. So I started talking about solutions towards the end last time here in chapter 10. And again, remember, as we've talked about earlier, there's two parts to the solution. There is the solute, which is the smaller part. And there's the solvent, which is the larger part of the solution. And again, solutions are typically, again, those guys that will get the aqueous symbol next to them. Means obviously they are a homogeneous mixture. Everything sort of mixes really well with each other. And when we talk about sort of solubility, a lot of sort of solubility of one substance in another does relate a lot to those intermolecular forces that we talked about. And again, those intermolecular forces are those forces between two molecules. They could be two of the same molecules, could be two different molecules, but it's basically how they interact with one another, as we talked about. And the basis of that sort of interaction is really that sort of opposites attraction, that positive and negative attraction between the two molecules. And what we see in sort of solubility is the idea of like dissolves like. And really what that means is, as we talked about, that things that are using the same sort of intermolecular forces will typically be very soluble in one another. So something is using hydrogen bonding, somebody else is using hydrogen bonding, they definitely should mix. Somebody's using dipole, they should also mix, sort of nonpolar and nonpolar, they really should mix. So it really is, in most cases, in terms of solubility, things that are soluble, if you got like a polar and a polar guy together, ionic and polar, as they can do that sort of ion dipole interaction, and nonpolar and nonpolar things will both be using really those dispersion forces, and will make them soluble in each other. Again, really insoluble is a lot of times when you sort of cross over sort of that polar and nonpolar. And, there's a sort of example we used a number of times is, again, that sort of oil and water sort of example. Again, oil is going to be using something like dispersion forces, which are those weak temporary type forces, while water definitely wants to use hydrogen bonding. So again, over that long period of time, they're not going to be able to maintain that interaction, and they typically be insoluble in each other. So things definitely become soluble in each other when they're using really the same type of intermolecular force that they use with themselves. And we have run into a problem of insolubility when we sort of really mix those things together. It's also why in certain cases, water is not the best solvent in all situations, because again, if you try to use water as a solvent for something that is polar or ionic, it's going to work really well because they're going to be able to interact. But if you try to use something like water as a solvent for something that is non-polar, they're not going to be able to sort of interact with each other. So it would be a really bad solvent. So I think we talked about using something like iodine crystals, for example, with water. That's going to be sort of a no-go, as that is non-polar. That obviously is polar. So we're going to be using different sort of interactions that occur. But if you took some potassium permanganate sort of crystals there and put it in with water, you're going to be good, as that's ionic and that is polar water. And they're going to be able to do this sort of an ion dipole sort of interaction, and they're going to mix really, really well. So although we oftentimes think of water as sort of the solvent used for a lot of things, in certain cases, it's really not the best thing to sort of use. Any questions on any of that stuff we talked about there last time? Okay, so I think where we left off here is right about here with the idea of hydrophilic and hydrophobic. And some of these interactions that occur between different molecules are either sort of water loving or sort of water hating. And hydrophilic is basically water loving. So those are interactions on molecules that really do like water. And that could be a region on a molecule, not necessarily the entire molecule. And it could also have regions that are hydrophobic, which is water hating. An example of that, again, is the nonpolar part. So we do come across a lot of molecules, especially a lot of organic molecules, for example, that have kind of two regions on the molecule itself. It could have a part that is sort of polar, and it could have a part that's really non-polar. And we have these different sort of regions on the same molecule, which allows a molecule to have some different sort of interactions that could occur. So for example, ethanol, as we drew, I think the other day, if we draw ethanol here, looks something like this again. And it's really an organic molecule. It's an alcohol. And what makes it an alcohol is really the presence of this OH group. And this OH group, again, as we talked about, is pretty much what you see in water. And it is a polar region here on ethanol. The carbon and hydrogen part here, again, going to be a non-polar sort of region. And as we talked about, I think yesterday, something like ethanol is going to be soluble in water because it does have that OH group there that is polar, which allows it to hydrogen bond with water really well. And it's not a tremendously large molecule, so it's able to really interact. And I think I drew yesterday like one octanol or something like that, which had a bunch of carbons on it. And again, as you really build out a lot more of that sort of non-polar region on molecules, it has a very big effect on solubility, and you typically will see it drop a lot. And a lot of times in something like organic guys like this, usually that kind of 4 to 5 carbon or more sort of region is where you start to see a lot of drop in terms of solubility. Again, because that non-polar part becomes really large and it doesn't allow it to interact really well. But having sort of different parts on a molecule like a hydrophobic part or a hydrophilic part of the molecule can be very useful. And that is pretty much to deal with soap, for example. And when we have soap, as we might have looked at previously, soap has a really long chain. And I'll draw out all the hydrogens, but pretty much all this part here are carbons and hydrogens, usually longer than this, maybe about 18 or so going on here. Maybe I will draw out the hydrogens and a bunch of chain kind of continuing on. And on the sort of other end of soap there, it has this sort of carboxylic acid group here, which is a polar part. So this again is the polar head of soap. This part here, which is all carbons and hydrogen, is the nonpolar, sometimes referred to as the nonpolar tail of soap. And again, actually, in sort of a soap molecule like this, it has sort of a hydrophilic region, which would be where the polar part is. That's going to be the part that's going to work really well with water because it can interact with it. Actually, through hydrogen bonding there, it can do a little bit of that action. And on the non-polar part of soap, that's going to work really well with dirt and grime, which is typically non-polar. So it's actually pretty to our advantage here in soap to have actually both of these regions, because it's really what gives soap sort of its ability to work. Again, the dirt gets basically surrounded by that sort of non-polar part of soap. If I just draw it as lines, and that polar part of soap, which would be on the outside when it kind of surrounds our dirt, is the part that really likes water. So that works really well because, again, typically we do wash off the soap with water, and it does so by basically trapping the dirt. And then when we wash the water, the soap and water mix, taking the dirt with it, and you are clean. So having, kind of these two parts to the molecule, two regions of the molecule, has an effect on sort of its abilities or properties and even its functions. So something like soap works really well because you got the mixture of sort of non-polar and polar together. As I mentioned yesterday as well, if you had something like an alcohol there, like ethanol, or that had more OH groups, that also increases the solubility. Again, it gives it more regions to interact with water in there. And that's kind of similar to what happens with something like sugar, for example. As we saw, sugar basically has, a lot of OH groups basically spread out all over it. And everywhere there's that OH group, it gives it a place to interact with water really well, even though sugar is non-ionic, but is still very soluble in water. Any questions on that there? So again, here we have octane, which is basically 8 carbons and hydrogens all together, and that is definitely non-polar. Here we would use carbon tetrachloride, which is also nonpolar. Again, if you drew the carbon tetrachloride really quickly, you see it is our symmetrical geometry and going to be nonpolar. So those two are going to mix really well together. But again, here, if we take gasoline, which is also nonpolar, and put it there with water, which is polar, again, we will get that separation out. And typically speaking, when you take something that's more organic, which is a lot of what nonpolar molecules are, with something that's sort of water-based or aqueous, usually the organic stuff is on the top there floating and the water is on the bottom, sort of based on the difference in densities. So when one substance does obviously dissolve in another, it is said to be soluble. Yesterday, we also talked a little bit about some other terminology that's sometimes used when we do liquids and liquids, which is miscible. Miscible means that two liquids basically mix together. It's basically the same idea as soluble. And also immiscible, we talked about with liquids, when you have two different liquids that do not mix, they're immiscible in each other. They're not soluble in each other. And that's also what happens, obviously, when we take one substance that does not dissolve in another, it's going to be insoluble in each other. There is usually a limited solubility of one substance in another. Gases are usually always sort of soluble in each other, and that is because, frankly, they're flying around, right? So as they're flying around, just by that process, they are mixing, and they're mixing with each other. So they would be soluble in each other. Some liquids are always mutually soluble in each other. So again, polar and polar. And as I mentioned before, nonpolar and nonpolar are also going to be soluble in each other. Sometimes people miss that one because they think nonpolar is going to be insoluble and stuff like that. But again, if you have two nonpolar guys, they're going to be able to interact well with each other in terms of solubility. So as we talked about, things with similar structure gives us our like dissolves like sort of idea. The solubility of a solute in a solvent depends on the temperature. The higher the temperature, the larger the solubility of a solid in a liquid. And that is also sometimes what people will tell you to do if you are trying to dissolve something like a solid in, say, water or something like that, and it's not dissolving, kind of heat it up a little bit. When you heat it up, you're doing several things, right? But obviously by heating up, you're providing a lot of energy, right? And the idea there is that solid's going to gain some energy. It's going to allow it to sort of dissolve and separate a little bit more and get everybody moving a little bit more, some energy, and things will start to dissolve. The solubility of one substance in another is dependent on temperature. So typically speaking, in general, the higher the temperature, that more more solubility you have for things that are solid in a liquid. And the opposite is true as well. When you lower the temperature, you typically have a lower solubility of a solid in a liquid. That happens also for the opposite sort of reason. You lower temperature, has a lot less energy, right? So things aren't moving as fast. Going to take a lot longer for things to sort of dissolve, and less of it will be able to sort of dissolve. At a lower temperature, you have a larger solubility of a gas in a liquid. And that's just the basic idea of, if we have a liquid and we have a gas molecule in the liquid, at a lower temperature, our gas molecule should be traveling slower, which means it's going to stay in that liquid phase a little bit longer than it would. If we had a higher temperature, our gas molecule would be flying around a lot faster, and obviously would not stay in the liquid phase as longer. In terms of gases, the solubility also depends on pressure. Higher pressure, we have a larger solubility of gases, and that goes back to our friend Boyle, right? And that's because when we have a large pressure, we typically will have a smaller volume, right? And thus, if we have a sort of smaller volume, our gas molecules are definitely near each other for a lot more period of time, and they should probably be mixing more so than if you had a lower pressure, which means you have a larger volume that gives everybody more space to sort of fly around in. They're not going to be coming in contact with each other as often, and you'll have a little bit lower of a solubility that would occur in that case. So when we talk about solution, there's some different ways that we can describe a solution. And as I mentioned, based on temperature, there is a limit to really how much you could kind of throw into a solution or really a solvent to get it to dissolve. A very simple example of that, right, is like, if you take water and you take a couple sugar packets, you can get them to dissolve, right? But if you took the Costco size of sugar and dumped it into a glass of water, at some point, it's not all going to dissolve, right? It's all going to basically pile up on there. So even though it is technically soluble, there is a limit to how much that solvent can sort of hold, if you will, in terms of allowing it to dissolve. When something does dissolve, right, it oftentimes, if it's a solid in, say, a liquid, we oftentimes don't see the solid anymore, right? But we do know that it is really still there, right? When you make a solution, that solute that gets dissolved in is still there. And again, a simple example of that is something like salt water. When you look at salt water, right, it just looks like water. It's all dissolved. And you can heat up the salt water and evaporate off the water, and you'll be left with the salt coming back in its solid form. So what happens, right, is that stuff that's getting dissolved gets trapped in all that water matrix, right, of all the water basically surrounding them, and it's no longer visible to us with our naked eye. So when we put way too much sort of solute in a solvent, we get really a solution that's known as saturated. And a saturated solution is a solution where pretty much you hit what is sometimes referred to as a saturation point, that you pretty much have gotten at that particular temperature all the solute that you could get to dissolve in there. So you pretty much hit the point where you hit the maximum amount of solute that will dissolve in that solvent. What would happen in that case, if you continue to try to dissolve more of your solute at that particular point, it would stop dissolving. And again, kind of like my sugar example there, it will start to pile up and you won't be able to get it to dissolve. Now, if you need to dissolve more, you could heat it up, right? And then you would be able to dissolve a little bit more, but at a particular temperature, keep the temperature constant. There will be a point where you pretty much hit the maximum that you could get to dissolve, and that is a saturated solution. The opposite of that is an unsaturated solution. And in an unsaturated solution, you pretty much have not hit that point yet. So you have not hit the point where things will stop dissolving. And that means that you can continue to take some solute and get it to dissolve in that solution, or that solvent really, to make that solution. And you continue to get the solute to dissolve until you hit a saturated solution. So unsaturated solutions before a saturated solution, and you can continue to basically let it dissolve and let it dissolve until it will not dissolve anymore. And that's sort of how you know you kind of hit a saturated solution for sure, because you're scooping in your solid and it no longer is dissolving. So you pretty much hit that point. In 200B, there's an experiment where you have to make sort of a little saturated solution in your test tube. And that's pretty much how you know. You keep scooping until it kind of doesn't dissolve anymore. You got some solid left over. You definitely have a saturated solution at that point. There's also another type of solution that you could have, which is a supersaturated solution. And supersaturated solutions basically contain really more solute than they should have in a saturated solution. So it kind of has in a supersaturated solution, you kind of have a solution that pretty much has kind of too much solute dissolved in it. So a very common experiment they used to do years ago, and a way that you can make a supersaturated solution is you could take something, for example, like sodium acetate, which is a commonly used for this. You could take some sodium acetate and dissolve it in a bunch of water. And while you're doing that, you can heat it up. So as I'm heating this water and putting my solid in there and getting it all to dissolve, I am now definitely increasing the solubility of that sodium acetate in the water because I'm heating it up, which means I'm going to be able to, in this sort of heated up version, get a lot more solid dissolved in there than I would at room temperature, right? So as I'm heating it, it's going to allow a lot more of that sort of sodium acetate to dissolve. So I'm going to make a really saturated solution, and even more so here as I continue to dissolve that. After you sort of do that, what you typically will do is then kind of take your solution off the heat and just kind of let it sit undisturbed, basically. Kind of don't touch it. And you basically will have a solution at this point. Now that solution is going to start to cool down. So what happens to my solubility of my solid in there? It should now start to decrease. Problem is I already dissolved it, so it's still in there and it's still a solution at this point. So as that temperature of that solution starts to come back down, you will still have a solution. You'll have a very unstable solution at this point, because pretty much what you will have is now a solution at, say, a lower temperature that should only have a certain amount of solid dissolved in it, but you already got it all dissolved by heating it up. And the problem with that is the solution is not going to be really happy. And it's so unstable that, frankly, you can make all that solid come out of solution by really just taking just a super small crystal of whatever you dissolved in there. If you just drop that one little crystal in, it's going to go, whoa, that's like too much solid now at this lower temperature. And what will happen, it will go from a solution, which is liquid sort of state, and you'll see all of the solids start to come out of the solution. And basically you will end up with pretty much a rock hard solid at that point. It is so unstable. I've done this experiment many times, or demonstrated this experiment many times, that it is like if you take like the flask, if you did this in a flask or something like that, and you just accidentally knock it a little bit or move it too much without even adding anything else, all the solid will just start to come out. I've done that before. Here's your demonstration, taking it out and like putting it down, like it all just comes out. So it creates a really, really unstable solution when you kind of make a lot of times a supersaturated solution, because you really have a solution that has way too much solute dissolved in it, and it doesn't want to stay that way. So any little sort of change to it is enough to sort of throw it over the edge and allow that solid basically to come out of solution at that point, because it is too saturated with that solute that's in there. They used to do this experiment in test tubes at colleges, and they would have you put your thermometer in there, and then they would have you make it solid again. And then people had like a lollipop of a thermometer. They're like, how do I get it out? You know, and stuff like that. So after many broken thermometers, they decided not to do those experiments too many times in school. All right, so supersaturated solution in terms of equilibrium is a little front thing for 200B, but basically you just have way too much solute dissolved in there versus an unsaturated solution. Here's that actual experiment that I was just talking about. So this is basically the sodium acetate, and it is a solution, supersaturated solution. You could barely see it, but they're just dropping like just a smidge of what was in there, and you can start to see that's enough to make it go not so happy. And that's actually the solid, or the solute, coming out of solution. And again, at this point, it's going to be pretty much rock hard there at that point, as all of that sort of guy comes out of solution. Now, when we talk about the pressure and in terms of the solubility of gases, external pressure does have an effect on the solubility of a gas. Henry's law is a formula or a relationship that says the solubility of a gas in a liquid is proportional to the pressure of a gas over that liquid. This is basically like the soda can sort of reasoning here, what happens with a soda can. C is the concentration, so that is molarity, moles per liter. Sometimes people will use S instead of C, and S is the solubility or molar solubility, which is also surprisingly moles per liter, which is basically the same thing. So sometimes people refer to this as the molar solubility, or some people will just refer to it as the concentration, but it's basically molarity in each of those cases. P is the pressure in atmospheres, and K is the constant, or Henry's law constant, and it is based on the gas that you are dealing with. So this is sort of the soda can example. What I mean by that is, in a soda can, right, you have a lot of CO2 dissolved in the liquid part of the can because it's under a lot of pressure right before you pop the top. So under that lot of pressure, you will have a lot more of your CO2 basically dissolved in the liquid part, along with all your other soda parts. And when you pop the top, you're doing two things. You are releasing the pressure, right? Which means the gas molecules are now going to feel less pressure, which means they will escape the liquid part of the soda can a lot easier. The other thing that you do when you pop the top on the soda can is, as they are escaping, you also giving the CO2 molecules, right, an escape route out the top of it, right? And what happens when the CO2 molecules escape your soda and you leave it open for a while in a can of soda, you go back and taste it, it tastes a little flat, right? And that's because the CO2 molecules with the less pressure can escape the liquid part, and you give them an exit strategy there through the emergency exit on the top there. And obviously as they go out, air blows them away, they don't come back in, right? And your soda eventually ends up being flat because of that, right? And that is why when you have, say, a soda in a plastic sort of container, right, with the screw cap lid, it stays fresh a lot longer, right? Because you have the cap on it, right? It doesn't allow all the CO2 to sort of escape. They may be able to escape the liquid part, but it can't escape the entire container. So it'll stay fresher a little bit longer than a can that is sitting out because it doesn't obviously have a top to keep that CO2 in it. So Henry's law sort of describes that. And here's some constants, and you have a similar one in your book. And again, it is different for different gases there. And there's a much better example of my soda can explanation. But again, under that high pressure of when this is closed, it's going to have a lot more of the CO2 dissolved in that solution, keeping it a little bit more bubbly. And again, as you open it up, obviously you give it an escape route for it to leave. So why don't we try one? What is the pressure of CO2 that is required to keep a CO2 concentration in soda at 0.12? And our K value there for CO2 is 3.4 times 10 to the minus 2. So give that a go, see what you come up with. Okay, so if we look at this, we're going to use our Henry's law. And again, you can use S is equal to Kp, or if you want to use C is equal to Kp. Again, C or S, basically molarity. Again, S is molar solubility and C is concentration, which are both molarity in this case. In this case, we're going to solve for the pressure. So the pressure here would be our molar solubility divided by K. And in this case, we're looking for a concentration, which is our molar solubility of 0.12. Once again, you would go to a table, obviously, to find out, like we saw in the previous slide. And again, specific for the gas that you're dealing with. So you want to make sure, obviously, that you look it up for the proper gas. You also want to always make sure, obviously, unit-wise, everybody's sort of okay in terms of the units. And in this case, the molarities here will cancel, and our atmospheres will come to the top as we flip it over. And it looks like we'll need something like 3.53 atmospheres, which is a lot more pressure than normal pressure of 1 atmosphere, right? Which is why our soda pops when we open it up, right, under that pressure. Any questions on that there? Okay. All right, so we're going to talk about are really more so a review of some of these different concentration units that we talked about earlier when we were talking about, I think, titrations and all that, which was sort of out of this chapter. But we're going to talk about these units again, just to make sure, again, everybody's on the same page. We'll kind of go through them a little bit quicker than normal, since we kind of already seen some of these examples, or most of these examples here. Remember that as we talked about, there's a few different sort of percent concentration units that we see with solutions. And this is our percent mass to mass. And again, that is our mass of our solute over our mass of our solution times 100%. Remember, we also talked about a couple of other sort of percent concentration units that we see a lot, our CAN-C, which is percent volume to volume, which is our volume of solute over our volume of solution times 100%, and also our percent mass to volume, which is another unit, which is the mass of a solute over the volume of a solution times 100%. Remember, out of these three, really the one that you do want to watch out for, right, when you're using it is our percent mass to mass, as that is, again, made up both of the solute and the solvent. So you want to make sure that you get both of those things together. And as we talked about and saw previously, it is very common in these type of problems when you're dealing with percent mass to mass that information is given to you separate, the solvent and the solute sort of mass. So you want to make sure you always get that. On the other two, the volume to volume or the mass to volume, A lot of times you're given the volume of the solution, so you don't have to worry too much about sort of the solute and solvent. You could, but in most cases, it's usually just that percent mass to mass that you have to worry about it. Also, a reminder that if you are given a percentage of one of these guys, as we talked about, you basically can turn that into a usable conversion factor. That would be like 4.5 grams of calcium chloride in 100 grams of solution. Or in 100 grams of solution, there is 4.5 grams of calcium chloride. So again, as we talked about, you could kind of use those as conversion factors. If you're given the percentage, you could take it more like a dimensional analysis sort of unit conversion type problem. Or you could obviously plug and chug into those formulas as well, as we saw. Basically, it'll work out the same. So obviously in this one, like we saw, and we did this example earlier there when we were talking about titrations and solutions a little bit earlier chapter. But remember here, we have 2.5 grams of calcium chloride, which would be our solute, and our 50 grams of water, which would be our solvent in this case. So when we're calculating our percent mass to mass, our mass of our solute divided by the mass of the solution times 100%, we would have our 2.5 grams, which is our solute. And again, here we would need, in this case, to add both of those numbers to get the solution part of it, and then times it by 100%. Again, very common, as we talked about previously when we did this example, people really oftentimes will just divide by the solvent without getting that solution mass. So 4.76%, I think, is what we got there. This is calcium chloride in this case. Yeah. Any questions on that one there? Now, again, we also saw one where we are given that percent composition by mass, or percent mass to mass sort of value given to us. And again, we can turn this into a usable conversion factor. A reminder that the solute in a solution, as we've talked about, is really the name of the solution. So in this case, we have a hydrochloric acid solution, and we're looking for the mass of the hydrochloric acid, which means we should be looking for the mass of the solute in this case. So again, you can, as we talked about, either plug and chug into this equation, which means that you would have 37.2% equals the mass of the HCl divided by our mass of our solution, which is 35.5 grams times 100%. We would multiply the 35.5 to the other side and divide by 100. So multiply and then divide, right? And if we do all that, 37.2 times our 35.5 divided by 100, it gets us about 13.2 grams of HCl would be dissolved in there when you do that math. Again, this is the one I think I did previously, more of a conversion factor sort of way. Again, that 37.2% means you would have 37.2 grams of HCl and 100 grams of solution, which means you can just set it up like a dimensional analysis where you take the 35.5 grams of solution using our percentage as a conversion factor. And those cancel out, and obviously you would get the same here. This is really the same math as you did here. So again, you can do it the same way, either way in that particular case. Any questions on that one there? Now, molality, I'm not sure if we did talk about molality yet or not, so let's talk about it more here officially. Molality is another, again, sort of unit of concentration. And again, it should not be confused with molarity. So molality is abbreviated with a little m. And again, that doesn't stand for mass, but it is the moles of the solute over kilograms of solvent. And I do think we talked about it, but just to make sure. So molarity, which is capital M, is moles of solute over liters of solution. And molarity and molality is again different. One is kilograms of solvent on the bottom, which is the molality, and the other one is liters of solution. The thing that ties both of these together are the way that you oftentimes need to convert between the two of these is the density, perhaps, of the solution. It allows you to kind of go between the two if you need to do that in some case. So just like we call molality molar, molal is sort of how we refer to something that is the molality of a substance. And we're going to see molality here in a second and colligative properties a lot. It is used in those type of calculations. But again, it is different than molarity. And very oftentimes people get those two sort of confused when they look at it. So if we were to do this, we want to calculate the molality of a solution that's prepared by taking 61.7 grams of C3H7OH and 175 milliliters of water. This is going to be our solute. So here we would need to convert it into moles, as the molality again is our moles per kilogram of solvent. So here we would have, that I scribbled on it there, but I think that is that is 3 carbons at 12.01. We got 8 hydrogens at 1.008. And we got an oxygen at 16. And that will give us a molar mass in this case of 3 times 12.01 plus 8 times 1.008 plus a 16. It gives a 6009 molar mass. So converting our 61.7 grams of C3H7OH into moles gets us we'll call it 1.027 moles. At this point, we have our water, which is our solvent in this case, and water works okay as a solvent in this case because there's only 3 carbons and there's that OH group, so a little propanol action happening here. And we have the density here, which is mass divided by volume. In this case, we will use the density equation to find mass, which is volume times density. And the volume is 175 milliliters for our water. And our density is 1 gram per milliliter, which means I got about 175 grams of water. Remember, though, that when you use the molality equation, it is kilograms and not grams. So I got to do a little conversion there, dividing by 1,000, right? So take 175 grams of water. There are 1,000 grams in a kilogram. Gets us 0.175 kilograms. Now to get our molality, we're going to take our moles divided by our kilograms of solvent, and that will get us, looks like I hit the right button here, like give us a number maybe. There you go. We'll go with 5.87, and you can leave this as moles per kilogram, or you can do 5.87 and little m as well here, as how you leave it. So molality does come up a lot in what we're going to talk about here at the end of this chapter here, which is our colligative properties to calculate the molality. Sometimes the molality is given to you and you need to use it maybe to get like the amount of solvent or maybe the moles of the solute that's present. Sometimes you need to calculate straight up the molality of something to use it for another formula. So it is used a lot in colligative properties that we will talk about here in just a sec. Any questions on that calculation? And lastly here, which I think we also talked about in that third chapter with solutions, we also saw it obviously with gases as well. Again, a reminder, mole fraction, which is represented by X. It's basically like a percentage without the percentage part. So it's the moles of what you're interested in divided by the total moles. And again, here we don't multiply by 100. So it just gives us like a point something type number when we do our mole fraction. So again, like this one that we did here, we were looking for the mole fraction of methyl alcohol. We would take our moles of it divided by the total moles, gives us 0.261. Basically 26% of it is made up of that moles of that particular guy. Any questions on any of these sort of concentration type units? Again, these are ones that hopefully should still be familiar for you, since we just did it not too long ago. And obviously the big one should still be familiar to you, I hope, which is molarity, which is moles per liter. And again, that is different than molality that we just looked at. And again, density is sort of the value that you could kind of use to go from one to the next if you needed to. So we're going to see some of these sort of properties, and really more so, I would say, probably the molality and the mole fraction is going to be seen a lot, is in colligative properties. So let's talk a little bit about that. So colligative properties of solutions basically is dependent on the number of particles that are present. So the number of particles that are present in, say, a solvent will have an effect on properties of, say, that solvent. So for example, if we take something like just pure water here, right? And if we have just pure water by itself and we wanted to boil or maybe freeze, say we wanted to boil in this case, right? As we want it to boil, it's going to basically start to escape the rest of the water there by getting that energy and getting out there. And really in this particular case, it's got kind of a free path, if you will. The only other thing in that sort of solvent is more water molecules. So it's got kind of like a free path to the outside to let it boil. Now, if you take some water and maybe you sprinkle in there some salt or something like that. So you got some, say, sodium chloride ions now floating around in the solution. You also have them now surrounded by the waters that's going to surround them and let them dissolve. As you go to heat this, you now got a lot more kind of stuff in the way for it to try to escape out of there. And it's going to take a lot more energy to kind of move itself away from all these things so it can escape. And what we'll talk about, what we're going to see is, you know, something like boiling point, it will actually elevate the boiling point. So instead of boiling at a lower temperature, it's going to actually boil at a higher temperature, because it's going to take a lot more energy for it to sort of get itself out there. Now, same thing is true if you had that situation and you wanted, say, to freeze up the water, right? So now you got all this ions and stuff floating around in there as well. So when you go to freeze, right, we have to sort of remove energy, right? So as it has to remove energy. And then as it removes energy, these things, water molecules, need to kind of get together. But once again, you got a lot more kind of junk in the way of that process. So what happens is it takes a lot more energy to sort of be removed from that process in order for those guys to come together. The result of that, as we will see, is basically a lowering of the freezing point. So the freezing point gets lower than it normally would freeze when nothing's in the way, and can just kind of release all that stuff and kind of come together in the solid phase. So as you put things into a solvent, say like water or other solvents, you are also changing the properties of that solvent from where it will kind of normally boil, where it may normally freeze. Also things like vapor pressure as well, right? So vapor pressure, which is the first sort of one that we'll talk about, is vapor pressure lowering. And the vapor pressure, if you remember, is the pressure above a liquid, right, caused by gas molecules that basically escape the liquid phase. Remember that at the surface of a liquid, we got that constant sort of escape of liquid molecules into the gas phase, and we also got guys dropping back in. So in this case, the less of the intermolecular force that we have, or the weaker the intermolecular force, right, we're going to get a higher vapor pressure, because those guys are going to be able to escape, as we talked about, the solution. And you would have a lot more gas molecules above the solution than you would inside of it, if you will. And in a situation where we have a much stronger intermolecular force, it's going to hold those guys in the liquid state a lot longer. It's going to take more energy for them to break through. And that means there's going to be less of those guys able to sort of break through and get out into the surface and above the surface. And you would have less gas molecules at that point and a lower vapor pressure. So the vapor pressure of substance depends really on the nature of the substance and also the temperature. And when you add a solute to a substance, the vapor pressure is lowered because the molecules of the substance cannot evaporate to the surface as they could without that there. So again, by dissolving something in here, whatever it may be, an ionic thing, some other thing dissolved in there with it, again, it creates sort of this pathway where it can make it a lot harder for it to escape the liquid phase at the surface for sure. And that results in a lower vapor pressure because there's going to be less of those guys escaping into the gas phase. So we'll have less gas molecules above the liquid and a lower vapor pressure. So this is PZ is equal to XZ times PZ naught, and PZ here's the vapor pressure of the component in the solution, and P naught there is the vapor pressure of the pure substance, and our X here is our mole fraction. So again, that's our mole fraction that we just talked about. The vapor pressure lowering may be defined as the vapor pressure of the pure substance minus the vapor pressure of the solution. So that's the change in pressure, which again is kind of where it started minus where it ends. In this case, where it ends will be less than where it started. And that's why we're subtracting it in that fashion. So why don't you try one? The vapor pressure of ethyl alcohol is 66.5 torr. Calculate the vapor pressure of ethyl alcohol in a solution if 0.2 moles of glucose is dissolved in that solution. Let's see what you come up with. Okay, let's take a look. So here we're dealing with vapor pressure. So we're going to use our vapor pressure lowering equation, which is PZ, XZ, and P naught Z. In this case, we're looking at the ethyl alcohol. And this would be our P naught there, as that is the normal vapor pressure of ethyl alcohol with nothing dissolved in it. In this case, though, we are going to take 0.2 moles of glucose. Glucose is what's going to be our solute, and it's non-ionic in this case. And what that means is, right, when glucose goes for a swim, it doesn't create ions, right? So when you toss it in there, you get one sort of molecule of glucose per one that you toss in there. And that's different than, say, an ionic thing. When you toss it in there, it breaks apart into a bunch of ions in that particular case. So here we want the mole fraction here of our alcohol, which would be the moles of our alcohol, which was 1.25. And we want the total moles, which would be made up here of our solute, really, and our sort of our solvent. And we would get 0.2 plus 1.25 moles. And that will get us here basically 1.45 on the bottom there, 1.25 divided by 2 plus 1.25 gets us basically 0.862. And now we could calculate the vapor pressure of our alcohol here in this solution, which would be our mole fraction, times the normal vapor pressure of just the pure substance. And in this case here, we will end up with 66.5, about 57.3 torr in this case, right? So we do see what we expected to happen in this particular case. We dissolve this glucose in there. That's going to, frankly, get in the way of everybody trying to get out, right? Which means we're going to have less of those guys escaping the liquid part. We'll have less gas molecules above the solution, which means our vapor pressure should go down. And it did. It went from 66.5 to 57.3. So we lowered the vapor pressure because of all the interference of those particles of glucose basically floating around in that solution. Any questions on that one there? So vapor pressure lowering is one aspect of a colligative property as a result of particles that are in the sort of solvent, if you will, or solution. Another thing that can affect it, hopefully they got the same number, that's good, is there can be an effect on the freezing point of a solution. So as I mentioned earlier, when something comes to freeze, basically our solvent molecules are coming together to freeze up. And again, with nothing sort of dissolved in it, it's going to be allowed to sort of come together pretty freely, if you will. But again, the presence of some type of particles in that solvent, for example, will actually have the effect of sort of lowering the freezing point. So sometimes referred to as freezing point depression. So for example, water, instead of freezing at 0 degrees, will freeze at a lower temperature, like minus something. You know, like we make rock salt, right? To make ice cream, right? You put some rock salt, it gets really cold with ice, and it will freeze at a lower temperature when you do that. Now, again, it interferes with everybody coming together to make that nice sort of solid state. And there is a formula here that we can use to calculate the change in freezing point temperature, and that is what the delta TF stands for here. That's the change in freezing point temperature. Now, that is not what a lot of people sometimes confuse with being when they do use this equation. That is not the actual freezing point of the solution. It is actually the change in temperature, basically, or the change in degrees of the freezing point, times Kf times M. Now, M here is our molality, so that is our moles per kilogram. So that is our molality. Again, not molarity, but molality. And Kf is a constant, and this is what is sometimes referred to as the freezing point constant. Now, when you go to a table to look up the freezing point constant, and as we'll talk about in a second, the boiling point constant, it is all based on the solvent, not the solution. So the freezing point constant is based on the solvent. So also a problem people have is they go to a table like that and they go, I can't find my solution listed, like sodium chloride or something like that. And you won't find it because what will be listed in that is actually just a solvent. So if it's some type of aqueous solution, then water is your solvent, and you would want to look up water in that case. It may not always be water, but water is very commonly used in a lot of solutions, obviously, as we talked about. So water pops up a lot in these sort of calculations. But remember, if your solvent is actually not water, there's a couple of things that are different. For example, water freezes at what temperature? Yeah, freeze of water there at 0 degrees Celsius. That's the normal freezing point of water, right? But if your solvent's not water, you should look up in that table the other substance or solvent, and it also will probably have a different freezing point. So although 0 is used a lot and also water is used a lot, it does vary depending obviously on the substance used for the solvent. Now, when we talk about the change in freezing point, which is this guy here, it is important to do the calculation like this. And it will tell you the temperature at where the solvent will normally freeze minus the temperature of the solution that has the stuff dissolved in it. So because it is a depression, it will freeze at a lower temperature. So you want to do the delta T, or the change in temperature of the freezing point, as the temperature of the pure solvent where it freezes. So for water, that would be 0 degrees minus the temperature of where the solution will actually freeze. So it is important to do it this way, solvent minus solution, so you get the correct sort of subtraction or addition. And what I mean by that is, let's just say we did a solution like this, and we saw that it actually had a 2-degree difference in temperature. So if we did this calculation here and we calculate delta T as being, say, 2 degrees Celsius, that means that delta TF, right, would be our normal solvent where it freezes, which would be water in this example, versus our solution. So that means that the delta T in my example would be 2 degrees Celsius equals 0 degrees Celsius, which is normally where water would freeze, minus the temperature of the solution we're dealing with, which means the temperature of the solution in this case actually will freeze at minus 2 degrees Celsius. Yes, not 2 degrees Celsius. So it's really important to have that sort of solvent minus solution here. Otherwise, you may be saying it will freeze at 2 degrees Celsius, which means the freezing point actually went up, right, instead of down. So again, that will allow you, if you again, remember this to get the right sort of sign, if you will, on your freezing point temperature, or adjustment on your freezing point temperature. Question on that there. This formula here that we're looking at, again, is for when we dissolve non-ionic solutes in it. We'll talk about what happens when we do something that's ionic in a bit, but this is for non-ionic stuff. Now, boiling point is also affected by stuff that is dissolved in it, and it's actually boiling point elevation, which means by dissolving stuff in that sort of solvent, you will actually be raising the boiling point from where it normally would be. And again, the presence of that stuff that's dissolved in there, as I mentioned, sort of gets in the way of the process of those guys escaping the sort of liquid part into the gas phase. And the result is they need a lot more energy to kind of weave their way through everything to escape the solution. And the result of that is your boiling point will actually elevate. And we have an equation that is pretty similar to the freezing point. They are pretty much the same formula. This is the change in boiling point temperature. So that is the change in boiling point temperature is equal to Kb times M. Once again, M is our molality, which is our moles per kilogram. And Kb is a constant and is referred to as the boiling point constant. And it is also specific for the solvent. So once again, when you go to the table, you would look up it specifically for the solvent. So again, for water, normal boiling point is 100 degrees Celsius. By the way, in terms of temperature with these formulas, we leave it in Celsius, so we don't do any kind of Kelvin conversion usually. And that's because the constants are usually given to us in Celsius, so it all works out okay in this particular case. Now, the difference here is different. The change in the boiling point temperature is different than what we see with freezing point, because the boiling point here is going to elevate, which means it's going to be a larger number. When we calculate the change in boiling point temperature, it's actually the temperature of the solution minus the temperature of the solvent. So that is backwards of freezing point. Freezing point, we do solvent minus solution. Boiling point here, we do solution minus solvent, so that we get sort of the correct thing. So it's the same idea. So for example, let's say we did a calculation and we saw that it boiled at 102 degrees Celsius. I'm sorry, not that, sorry. We saw again that we had a 2 degrees Celsius change in boiling point temperature. So if we were to put this into our change in boiling point temperature formula, that's the temperature of the solution minus the temperature of the solvent. And if this was water again, in this case, that would be 2 degrees Celsius equals the temperature of the solution minus 100 degrees Celsius. We're now going to add that to the other side rather than subtract if you did it backwards, and you will get a solution that will boil at 102 degrees Celsius. So that again, sort of solution minus solvent for boiling is important, just as solvent minus solution is for freezing. It will get you adding and subtracting correctly when you are asked that. Again, very commonly people misunderstood when they calculate the delta T B here in this case. Again, that is not the boiling point temperature, but just the change between where the solvent would normally boil and where it will boil with the stuff that's dissolved in there. Any questions on that there? By the way, you put antifreeze in your car, it does both things, right? It actually will lower the freezing point in case you live in a really cold area, right? So things won't freeze. And if you live in a really hot area, which seems to be everywhere now, your car will hopefully not overboil, right? Because it will boil at a higher temperature. So that's why we add like antifreeze to our cars that have radiators and stuff like that, so that we don't hopefully overboil or freeze in those sort of extreme temperatures and stuff like that. Any questions on that? Again, this formula also for non-ionic sort of solutes that are dissolved in there. All right, so this is a table of Kb and Kf values, and sometimes you may have to obviously refer to the table, obviously on the exam or stuff like that. It will be provided for you, obviously, but in a book, you might have to look it up. And as you can see, again, it is all solvents that we see here. We actually have some non-polar solvents, right? And we also have some polar sort of solvents that are happening here. But again, the Kb and Kf values will be different depending on the solvents. And also, again, the normal boiling point and freezing points will change depending on the solvents. I would say we use water a lot. So these numbers, you will see a lot in these sort of calculations. So our KF, 1.86 degrees Celsius over molality for water, with a normal freezing point there of 0 degrees Celsius, and our KB for water, 0.512 degrees Celsius per molality, and our normal sort of boiling point being 100 degrees Celsius. But obviously, if we were using chloroform, we would have much different numbers, and even some that are negative, which is even more important to do sort of the change in freezing point or change in boiling point correctly. Because obviously, if you do it incorrectly, you may be, again, subtracting when you should be adding, or adding when you should be subtracting. Any questions on that there? All right. So why don't you try this? What is the freezing point of a 1.7 molal ethylene glycol solution? The KF there is one. Take a look at this one. So we're dealing with freezing points. So we would want to use our freezing point equation, our formula, which is our molality times R with our KF there. In this case, it's an aqueous. So the key there, aqueous, is water environment. So that is how you know water is the solvent here. And that is what you should be looking up. So again, sometimes those keywords is what you want to look for. In this particular case, they actually did calculate the molality for us, so we don't have to calculate it, but sometimes you do need to calculate it yourself. So we can just go right into our equation here. The KF, once again, from the solvent, which is water in this case, and timesing that by the molality, which was nicely calculated for us already. So our molality will cancel out. And in this particular case here, we'll end up with 1.86 times 1.7 gets you, we'll call it 3.2 degrees Celsius. Once again, though, that is not the answer in this case. That is just the change in the freezing point temperature. We're looking for what the solution's freezing point would be. And since this is the freezing point depression, which means that the freezing point will be less than the solvent itself, this is the one where we take the solvent minus the temperature of the solution. Since water is our solvent, the normal freezing point temperature for that is 0 degrees Celsius. So we would have 3.2 degrees Celsius equals 0 degrees Celsius minus the temperature of the solution. That means that the temperature of the solution will actually be minus 3.2 degrees Celsius. So again, not 3.2, but minus 3.2. Again, that is less than 0, which is what should happen in this case. Again, if you put 3.2, you're telling me that the freezing point is going up, which is, again, the wrong sort of direction for that. Any questions on that there? So this is one aspect at which you can sort of use freezing point or even boiling point sort of calculations to figure out, what the actual boiling point or freezing point would be of the solution by having that stuff dissolved in it. By the way, this is also a non-ionic, right, sort of substance. It's all carbons, hydrogen, oxygen, so that's covalent bonding. So when one of those goes for a swim, it's going to stay together, right? It's not going to break apart into a bunch of little things. It will all stay together. So another thing that we can use to our advantage of freezing points is to calculate something like the molar mass, which is grams per mole. And in this case, we're looking to calculate grams per mole of a compound if a solution of 12 grams of it is dissolved in 80 grams of water and it freezes at minus 1.94 degrees Celsius. So why don't you take a few moments, see what you come up with, and then we'll talk about how to. Okay, let's take a look, see how you're doing. So in this case, we're looking for something a little bit different. We're looking for grams per mole, which is the molar mass, but we really can use the information that's given to us, which is really the freezing point sort of information to help us sort of figure that out. First off, we dissect sort of what we got going on in the solution. Really, that's the solute, right? And that is the solvent there, which is water in this case. And we are looking for grams of this guy. So that is the grams part right there. So we don't have to do very much work to get to the grams part of it. Now, the moles parts can actually come from really the freezing point information. So in this case, if we do our freezing point equation, we have Kf times our molality in this case. Now, we do have the Kf because we do know that the solvent here is water. So we can look that up, which is obviously what this number is for. We do have that the solution actually freezes at 1.94 or minus 1.94. Now, you may be tempted to think that that is the change in freezing point temperature, and it is not. That is actually where the solution freezes. And the reason this is important is you'll have some negative action going on there that you probably don't want. What we know is, as we talked about, that the change in freezing point temperature is going to be the temperature of the solvent minus the temperature of the solution. In this case, our solvent is water, which means it normally will freeze at 0 degrees Celsius, minus the temperature at which the solution will freeze, which is minus 1.94 degrees Celsius. That gives us a change in freezing point temperature of positive 1.94, which is how we get rid of the negative in this case, so we don't have it where we don't want it. Any questions on that there? Now that we have that, we basically have the Kf and we have the change in freezing point temperature, so we can solve for the molality here. So the molality would equal the change in the freezing point temperature divided by the Kf, and that would give us 1.94 degrees Celsius divided by 1.86 degrees Celsius per molality. And the degrees Celsius will cancel, and that will get us 1.94 divided by 1.86. Call it 1.043, and this is molality, and that really is the same as 1.043 moles per kilogram of solvent in this case. Any questions on that so far here? Why is this going to be helpful? Because we're looking for moles, right? And right now we have moles of solute per kilogram of solvent. And we do know that the amount of a solvent that we have is 80 grams. So the mass of our solvent, which is water, is 80 grams, which means we could convert that into kilograms. 1,000 grams in a kilogram gives us 0.080 kilograms of solvent, which is this part. So we can use the molality and the kilograms of solvent to figure out the moles of our solute. So if we do that, we'll take 0.08 kilograms times it by the molality that we calculated from the freezing point information. Our kilograms will cancel, and this will get us 0.08344 moles, which is the bottom part of what we need. So now we have the grams. We use the freezing point information and the equation basically to get to the moles of the solute. All that's left is to divide those two. So the molar mass here will equal our grams, which was 12 grams, divided by our moles, which we got from our freezing point information. And I missed a zero there, 0.08344. Going to give us a molar mass of about 144 grams per mole. So by having the actual freezing point information and a little bit more information about how many grams of the solute there, we're actually able to figure out the molar mass of this particular substance based on how it freezes in that solution. Any questions on that there? All right, so I think we'll lay it up there for today.